We will now use the rules and properties of logarithmic and exponential functions that we studied in the last few sections to solve equations. So before we begin, let's remember that both the base and the argument of a logarithm must be positive. This is important because when we solve exponential and logarithmic equations, specifically logarithmic equations, we have to make sure when we get an answer, if we plug it back in, we don't end up taking log of a negative number. So there can be extraneous solutions that end up solving the final equation, but the original equation, when you substitute back in, you take a log of a negative. So it's something we have to check, so we must check our answers. So if we have a log base a of x equals y, so we know that our base, that a has to be positive, and that base, remember, cannot equal 1. And then our argument, the x, it has to be positive as well. So let's look at example 1. We want to solve a logarithmic equation, and we know it's logarithmic because we've got the variable here contained in the argument of this logarithm. So the left and the right side both have the same base, so I have two logarithms equal, so we know we have that property that allows us to now set their arguments equal. So we can say 2x plus 3 equals 3. Now we have a linear equation, and we can just isolate our variable x. So we'll subtract 3 from both sides. So we get 2x equals 0, and then divide by 2, and we get x equals 0. But we must check and make sure when we substitute this 0 back in for the x here, and that x is part of this argument, we want to make sure we get a positive number there. So my check, I want to substitute 2 times 0 plus 3, so that would give me 3. So I'm okay here. 3 is greater than 0, so I can circle my solution x equals 0. Now we can also solve or verify our solution graphically on the graphing calculator. So remember, we have the method of graphing the left and the right side of the equation and then seeing where those two graphs intersect. So if I'm graphed my left side as y1 and my right side as y2, remember that our calculator can only graph and evaluate logarithms with a base e or a base 10, the common log, so they can only do natural logs or common logs, log base 10. But also remember, we have the property, the change of base formula, that allows us to convert to any base. So I'm going to convert these bases into either e or 10. So just for our notes here, I'll use base 10, the common log. So I'm going to graph for our y1. Remember, we take the quotient. So we want common log 2x plus 3, and we're going to divide by log of 5. We could also do natural log of 2x plus 3 over natural log of 5. We'll get the same ratio. And then for our y2, we'll take the quotient of log 3 and log 5. Now when we enter these into our y equals editor here, we've got log 2x plus 3, and then we'll close the parentheses on that argument 2x plus 3, and then divide by log 5, and then here's our log 3 divided by log 5. So there's our two equations we're going to graph. I'll graph on a standard viewing window first, and we'll see if that gives us a good picture of it. So I'll go to Zoom Standard. There's our first, the left side, the y1, and there's the y2. So we can definitely see for y1 that ramp shape, and it certainly looks like here, this graph looks like it ends, but remember that's that vertical asymptote. And if we look at our second graph, we see that's a horizontal line. Well, that's a constant function. That's because the y2 here, there's no variable here. This is just a constant. Log of 3 over log 5 is just a constant value. So it actually, this is the ramp shape, the left side of the equation, and the right side is that horizontal line. So we're expecting that these would intersect when x is 0, and that certainly looks reasonable here, but we can check to verify, so we'll calculate. So second trace to calculate the intersection, option 5. So there's our first equation, log 2x plus 3 over log 5. So that's our first curve, hit enter. Here's our second curve, log 3 over log 5, hit enter. And then we'll hit enter one more time. And we can see that our intersection is, in fact, at x equals 0. So I am going to drag this screenshot into our notes here. And if you guys want to make a little sketch of this in your notes, that's not a bad idea.